All right. This is kind of like one of my first. This is my first video on. I have one on parametrizations. I'm still working on calculus 3 or multivariable calculus. We will be doing the flux across the paraboloid is equals 1 minus x squared minus y squared. So we are calculating the flux of the vector field f equals y comma x z across the paraboloid. That's the surface, right? 1 minus x squared minus y squared. So let's begin. Now I do have a mathematical plot here included in this video. I'll be doing another mathematical one. This is slice vector plot 3D. The calculations I'll have to do in a video 2. And my video 3 will have the Mathematica program I created. I did make one. It's above here in my transcript. I'll show y'all in the third video. Okay, so I'm going to go ahead and zoom in real quick so y'all can see this one I included, this slice vector plot 3D in Mathematica. You're going to want to put everything in just like I have it, okay? Make sure you're doing that so you don't have any errors. If you do, leave it in the comments. All right, let's begin because we have a time limit. So you're given a field y, x, z across a surface C. The first thing you need to do is parameterize your paraboloid as efficiently as possible. So instead of using u and v like you're used to, you can simply keep it as x and y. There's nothing too complicated here. It's just a paraboloid. I find it easier in some scenarios to use x and y. In other scenarios, it's u and v. I think through a little practice, you'll see which one's best in which or in any given situation. So we're just going to keep it x and y here. Respectfully. Now, I did include up above how it would look like in U and V, right? But it's just superfluous, right? So it's just going to be UV in this here. Pause it if you need to. I'm going back down, and we're going to continue on with this video. So with this one, you want to parameterize. You need a parametric surface vector equation. So that's going to be R equals X, Y, and Z. Now, Z is the surface 1 minus x squared plus y squared. I went ahead and distributed the minus signs out. And just so you know, that is your surface Z. You're going to want to put that Z component into your parametrization. Now, for later on when we do the integral in the second video, I will actually set up that integral in this video. I just won't do the calculation in the second one. This is going to be your parametrizations you're going to need to put in for the calculation part. Remember, x squared plus y squared is equal to r squared. I forgot to jot that down here when we do that, when we get to that stage in the game here. So first thing we do is we need our x partial, right, for this parametric surface. It's going to be 1, 0, minus 2x dx. And then your ry is going to be, of course, 0, 1, minus 2y dy. And at this point, if you don't know what's going on here, your Rx, you're just differentiating x. You're not differentiating y. So you're just going to get 1 and then that 0 and then negative 2x for your z component here, right? So with respect to x here and respect to x here as well as here, that's why I just went ahead and distributed the dx out of here like so. Now, just so you're not confused later on, that is going to be over here when we get finished doing our normal vector. I'll get to that portion in a moment. Let's do our ry. So with respect to y, that's 0 dy because there's no y there. So it's just 0 and you differentiate that. There's no y, it's just 0 and you differentiate y. That's 1 dy. Remember, I'm keeping it out here. And then you're going to go ahead and do the same thing here. That's a negative 2y for your z. Now, I'm going really fast. So if you need to slow down the video, that's fine. I apologize, but I keep making them and they're too long, especially with these types of calculations. So for your normal vector, right, you're going to want to do the determinant. You're going to want to keep in vector form. We're not doing any funky square root business out here. So there's your ijk. The first component we need to do our Cramer's rule on this. So you're going to omit I. And you're going to do the cross of j and k here. So that's going to be 0 times minus 2y minus a 2x in this direction, remember. So that's going to give you 2x for your ith component. For your jth component, what you're going to do here is you're going to omit j. Now remember, j has a negative sign that's understood out here in your plus and minus schemes for matrices, right? It looks something like this, right? And I'm not going to do like a three-dimensional one because I don't want to make any mistakes, but that's definitely going to be like so. So there's an understood negative sign here already. It's not there because I'm about to do the calculations. So It's going to be negative 2y, which is a positive 2y, minus a negative 2x times 0, which is just 0, right? So that just gives us negative 2y here, which is positive 2y. Now your kth component, pretty easy. Omit your k, and then cross these two. That's 1 minus 0. That's going to give you 1. Now, if any of y'all are wondering what happened to the dx and dy, yeah, sure, you could have put it here and done your cross product. I encourage you to do that if you want to, so that you kind of know where it comes from when we do our calculations and we switch to polar. That's your dA, right? Now, I'll get to that. So then now once we've done this, we've got our normal vector 2x, 2y, and 1, dx, dy. We're going to need to dot that with our f. Let me note a few things here. So, because I know there's a lot of points of confusion. Number one, that gets a lot of calculus through students in college is, why is there an n and a dA? Remember when you were doing single integrals, you already really kind of had your dx there? That's because you're not doing Riemann sums anymore, right? You're already kind of past that point. So that dx, dy, that dA, this whole thing right here is actually your NDA. I know they talk about normalizing and whatnot. We're not doing surface integration here. We're just doing dot products as well. But this is going to be your NDA for all intents and purposes. And you're just doing this dot product f dot n. Okay, now that I've stated that, your dA is going to be over here. That's your dx dy. Let me pull out a little bit. Okay. All right. So here's the deal. Now we need to take our dot product. Your integrand, do not bother with doing your x limits of integration, right? Here, and your y limits of integration, because we will be switching to polar. I'm just not doing it yet. So go ahead, and if you want, you can put an S there to denote that later on you're going to take care of that when you switch to polar. I didn't put my dx dy or dy dx here, so I apologize, but it does exist. We are going to switch that to polar in a moment. Now, when you take the dot product, guys, we know this at this point. This is the beginning of calculus 3. You're going to do y dotted with 2x, right? That's going to give you this portion. And you will be splitting this up because the dot product gives you the addition of each component. That means your integrand is going to be split up into 3 integrals because it's 3-dimensional. So y dotted with 2x is 2yx. And then, of course, x dotted with 2y is 2xy, same thing as 2yx or 2xy respectively. Now, the z part, if you're confused. When you're doing polar in class or u and v, you usually substitute those u's and v's or that polar ahead of time they teach you in this way. Don't do that, right? We're going to save that for the end. The reason for that is that you don't want a bunch of r's and thetas and cosines. I don't know about y'all, but when I see cos trig everywhere, it's just extra stuff to pollute my mind while I'm trying to get to that point. So it's kind of like if you are in any sport, you're really setting up your opponent. You're not for that end result. You're not doing it while you're at it. You're not jumping the gun. You're not being impetuous. I find that to be very impetuous thinking. So you definitely want to logically just keep it with x and y's. So that's 2yx, and x times 2y, or dot, is going to be plus 2xy. And then we're going to dot that z with the 1 here. So that's z. I know why they say z now, it's just easier. Okay, now you move on this way. I don't hear that a lot. So now, what is z? Well, z is our surface. Now, I went ahead and distributed that negative sign out because I want that r squared to pop out. I want to be able to see it. And that's what this is here, simply. I had to put it in parentheses. It looks kind of messy. It's about the only messy portion here, in my opinion. So dy dx is still there. Now what do we do? All right. Now, once we've had this, I want you to notice how easy this fast calculation was. It was really quick, in my opinion. And now we can switch to polar. Now, what is dy dx? Now, when we did double integrals, we know that dy dx is going to translate to r d theta. I remember this from double integrals. I will be doing double integral videos This is your little differential transformation here. Now, which is just a simple geometrical transformation, but with your differential portions. No big deal. Don't overthink that. So now you've got 4xy dy dx. Where did it come from? I added those together respectfully using algebra. And then now you've got the, well, where does the 1 come from, right? Where does all this stuff come from? Well, I want y'all to notice whenever you put your z in, that 1 comes from here. And it's minus something. So that means you have to split it up into another integral here. Pause the video if you kind of need to look at that. But it uses sum and difference identities of integrals, right? Once you made your z substitution. So, and of course your dy dx distributes to everything, so that stays. And then the last portion is that negative portion here of this last double integrand. That's the x squared y squared dy dx. I provided the polar transformation ahead of time. So now you're going to substitute everything in. Well, we know that x is equal to r cosine theta, and then y is equal to r sine theta. All right, so now at this stage of the game, all you have to do is substitute everything in. Now, do not forget to put in that dy dx transformation, right? It belongs to every integral, as we should know by now. That means I went ahead and put it in its form for you, kind of attached in here. So now your x is r cosine theta, y r sine theta, r dr d theta. That becomes r cubed cosine theta sine theta. Dr d theta, I distributed my r's, multiplied them as associative. And then you've got your 1 r dr d theta, that's r dr d theta, r dr d theta, that's pretty straightforward. And then your r squared gets multiplied times your r dr d theta. That becomes your r cubed r dr d theta. Now I went ahead and provided real quickly the actual calculation. So you, in case you're kind of out of time and you need to calculate this real quickly up here. So that way, instead of watching my second video, if you feel like you need to do this, that's fine. Try to get it to where y'all can see a little better. So I need to kind of, this is your double integrand for the first integrand, the first double integrand respectively. And guys, there's a little thing in math here, right? Odd and even. When you're integrating, you're going to get 0 if you do odd and even, right? When you do your theta portion. But you're going to want to do your r first, etc. Anyways, there's that calculation I'll be doing in another video. Pause it if you'd rather just kind of see the rubric here, whatever you call it. Now for this second double integrand, you're going to have all this. Go ahead and copy it down. Pause if you need to. That's pi. Remember the first double integrand was 0. And the last integrand here, the r cubed. You can see that little reverse upper triangular here. You're going to add them all together. Your answer is going to be pi over 2 for the flux, the total flux across S. That's going to be the lateral surface of the paraboloid is pi over 2. We did not do the cap, right? Just so y'all know, the cap calculation was not done. This was simply just the flux across the lateral surface of the paraboloid. I will be doing divergence theorem and proving it with all surface flux through the surfaces, respectively.